The next two videos, we're going to talk about the phase portrait for a forced harmonic oscillator, but really this part one of that is just introducing some things and then solving a problem so that we can actually compare with the real solution. So remember that phase portraits analyze systems. Phase portraits are for systems of equations. We don't have phase portraits if we don't have a system. But of course, if we have a forced harmonic oscillator, we can convert that to a first order system. A second order differential equation is a 2x2 first order system. And we'll do that in the next video. We'll make that more explicit. But we've mostly just been looking at solutions to those and like functions over time. So like what would a phase portrait look like? Our phase portraits, we'll introduce a second velocity variable, like we've done all of chapter 3 or whatever. And then our phase portrait is going to be in the YV plane. But phase portraits are going to be more difficult for us now because we're no longer looking at autonomous differential equations. Just like we had phase lines for autonomous differential equations, but you know, if our differential equation had t's in them, then, well, we didn't use phase lines anymore. Similarly, our phase portraits are going to be much more complicated because these are going to depend on time. And when we had phase portraits in the past, we said our solutions didn't cross because we had uniqueness. And we still have uniqueness here. But now time is happening in the phase portrait. So you could think of like having a phase portrait, maybe have like one phase portrait. But then imagine a little slider for time. And as time happens, each of these solutions moves. Okay? So phase portraits actually are now in YVT space. These phase portraits actually are in three-dimensional space now with t as our third variable. So it gets more difficult. But we're still going to be able to use numerical methods. We can still use Euler's method on these things. There's other methods that are covered in chapter 7. We will not do that. That we can also use to find graphical approximations of this. And we'll still just look at them in 2 dimensions. It's a little harder to see them in 3 dimensions. So we'll just ignore time and say that we're looking at like a projection of like, okay, if we flatten this out, what is it going to look like? And thinking of like a spiral staircase, spiral staircases don't cross. Right? If you have a spiral staircase, that staircase is never crossing itself. But if you project that and look at the spiral staircase just from above, it'll look like it's crossing. So we'll eventually have some phase portraits in this section that could look something like this. It's not actually crossing. It doesn't violate uniqueness. This is just like a two-dimensional projection of something in YVT space, and we're just not looking at the time component. Okay, so with that said, let's introduce an example, we'll solve it, and then we'll do more analysis of it in the next video. So I want you to solve y double dot plus 2y dot, and don't worry, it's not the same differential equation, plus 10y equals 4 cosine of 2t. So the left-hand side, let's forget about this for example, or for starters. The left-hand side is very similar damping as the last example that we did, but our spring constant is much higher, so relatively a smaller damping force. The last one was underdamped, so if we have a relatively smaller damping force, this is probably also going to be underdamped, but no spoilers. And the right-hand side has a different frequency. The right-hand side's, the force, the external force, is oscillating at twice the speed. It has a horizontal compression of 2. It's oscillating at twice the speed and at 4 times the amplitude, as the last one is before. Something else I see is I notice that our right-hand side, our forcing function, is a cosine. Euler's formula, if you remember, e to the I theta is cosine of theta plus I sine of theta. Similarly, our functions, we showed that if we have a complex valued function, right, that's always going to be a real valued function, plus I times the imaginary part, which is also real, of that function. And we said if the right-hand side is cosine, we use this. And we said if the right-hand side is sine, we're going to use this. So if you remember, in the last example, we looked at the imaginary part to come up with our particular solution. Here, we're going to look at the real part to come up with our particular solution, because it's cosine. If you're ever in doubt of whether your solution's a solution, do some quick derivatives. Check your answer. We should do that in this video too. Okay, so I would highly recommend you pause the video, find the homogeneous solution, find the complex solution, use that to find the particular solution, and use that to find the general solution. Using everything that we've learned so far in this class, you should be able to pause the video and do these steps. You can unpause every once in a while to make sure you're on the right track, but you should be able to do this. It should be hard, but it's good practice. Productively struggling is kind of the goal. So if this is the case, then we start with solving the homogeneous or unforced equation. We're going to look for eigenvalues. That'll be s squared plus 2s plus 10 needs to equal 0, characteristic polynomial. We can complete the square again. October can climb the green screen again. October, stop that. All right. And, or it can, yeah, let's complete the square, right? S squared plus 2s plus 1, subtract 9 from both sides. This is s plus 1 squared equals negative 9. We're going to, s is negative 1 plus or minus 3i, I believe. Okay, and we can use this immediately to get the general solution. So our general solution to the homogeneous or unforced equation, uh-oh, October laid down on my notes. At least she's not climbing the green screen. We're going blind. Is going to be k1 e to the real part times t times cosine of the imaginary part times t plus k2, same thing but with sine. All right, no problem. Homogeneous, done, check. Now, let's solve the complex version of this and find our complex solution, use that to find our particular solution of the real ODE, and then finally get the general solution. So we're going to do that. Oh, she's also laying on my keyboard. Life is exciting with this cat. So we're going to solve the complex differential equation, which is y double prime plus 2y prime plus 10y equals now, before we let the right-hand side just be e to the it. But we're going to modify that a little bit, because we don't want to look at e to the it. That has the wrong period and the wrong amplitude. So instead of just e to the it, let's make it 4 e to the 2it. All right, and I should have warned you when I told you to pause the video. I should have warned you this part was to be a little different. I tried to warn you about this stuff up here with the depending on the right hand side, but I forgot to warn you about this. So we're going to find our complex solution to this and use it to find our particular solution, because our particular solution will just be the real part of this complex solution. So we're going to guess that our complex valued solution is going to be a, which can be a complex number, times e to the 2it. And again, we choose 2it because we want these to match. Plug things in, look at the left-hand side, look at the right-hand side, see what we get. Take the second derivative, you're going to get a 4i squared, which is negative 4a e to the 2it, plus 2 times the first derivative is going to give you 4ai e to the 2it, plus 10 times the original function, a e to the 2it. And we need that to equal the right-hand side, but we'll simplify a little bit. Just like before, we're going to get minus 4a's plus 10a's. We're going to have 6a e to the 2it plus 4a times I e to the 2it. And again, just like before, we want these to equal. So we're going to try to write this left-hand side in the form of this right-hand side by factoring out an e to the 2it. That gives us 6a plus 4a times I, and that needs to equal 4e. So to equal the right-hand side, we want this to equal 4. So let's find it. 6a plus 4a times I needs to equal 4. Just like before, we'll factor out an a, and we'll divide, and we'll rationalize the denominator by multiplying by the complex conjugate. And I know I'm moving very fast because I want you to be really pausing the video and working on your own and then just catching up to hear explanations and then pause the video again. When you simplify like this, you're going to get 24 minus 16i in the numerator, and the denominator will give you 36 minus 16i squared, just plus 16. So our denominator is 52. So we get 24 over 52 minus 16 over 52 times I, which surely reduces. 52 is 4 times 13. So they're all divisible by 4. 6/13 minus 4/13 times I. And I'll check my notes. We'll move October to the side a little bit. Make sure that I did not make a silly mistake. And indeed, this is our A value. And remember, I said get very excited because once you know your A value, that can tell you everything you need to know about the long-term behavior. The modulus of this complex number is going to be our amplitude. So this squared plus this squared, square root, is going to be our amplitude. The theta for this number in the complex plane is going to be our phase angle. So that's going to be pretty cool. But we'll pause for a little bit. So we were looking for our complex solution, and we found it. Our complex solution is going to be yc of t is equal to a, which we could write like this, or we could use Euler's form and do some other things. So let's just do that, right? And to do that, we're going to move on to the next page. So this is our A value. Let's write this in polar form so we can write the complex solution more manageably. So if we do that, and again, you could also be using undetermined coefficients with sines and cosines to solve this. That would also work. You should get to the same answer, but it just might not look quite as nice. So if we put this into polar form, let's plot. It's much easier to put something in a polar form when you're graphing it. So if we do that, we say this is going to be the real axis, and this is going to be the imaginary axis. 6/13 minus 4/13 I. Maybe that's around here. Here, we'll zoom in a little bit. We know the x-coordinate, or the real part, is 6/13. The y-coordinate and the imaginary part is negative 4/13. We need the modulus, and we're going to need this angle. So we use Pythagorean theorem to get the modulus. We'll look at the square root. This is the modulus of A. Square root of 6/13 squared. Oh gosh. Plus a negative 4/13 squared. I do not want to do this, but I will because I'm trying to model good behavior. 36 over 169 plus 16 over 169 is, hey, 52 has come back. Square root of 52 over square root of 169 is just 13. And we have to simplify the square root of 52. That's 4 times 13. So we have this. Or if you didn't want a rational denominator, this is less writing. So that's the modulus. And again, I usually like to, so this is going to be 2 over root 13, e to the I times theta. We could find theta right now, but it's a lot less writing if we just save theta for later. So our complex valued solution was a e to the 2it, I believe. Let's double check that. Yep, it was. And we know that A is 2 over root 13. We immediately know the amplitude of our long-term solution, our forced response. It's 2 over root 13. And again, we can immediately find the period as well by looking at theta. So that is A. It's this e to the I theta. Again, as a reminder, this first part is A. Let's just simplify. Just like before, this is 2 over root 13. This is just 2t plus theta. So this really is just cosine of 2t plus theta plus I sine of 2t plus theta. This is our complex solution. And we only want the real part of this. Why? Because the right-hand side is a cosine function. If the right-hand side's a cosine function, you only need the real part. If the right-hand side's the sine function, you only need the imaginary part. Again, look at the symmetry here. See how it lines up? Similarly, in the complex plane, remember on the unit circle. Do you remember your unit circle? Any point on the unit circle, the x-coordinate is a cosine of that angle. And the y-coordinate was the sine of that angle. What's the x-coordinate? It's the real part in the complex plane. What's the y-coordinate? It's the imaginary part on the complex plane. So cosine has to do with real parts. Sines have to do with imaginary parts. Okay? So this immediately gives us our particular solution. It's just the real part. 2 over root 13 cosine of 2t plus theta. And we should find out what theta is finally. But this is really great because we know the amplitude, we know the period, and again, the period actually is going to match the forcing function all the time. And then we can find our phase angle right here, which can also be used to find the phase shift. Theta itself is the phase angle. The phase shift is negative theta over b. So negative theta over 2 in this case. And this is a much nicer particular solution. It took a little bit more work, but it's a much nicer particular solution than if you were using undetermined coefficients with sines and cosines. Because I know exactly what this looks like, or I will once I find what theta is. Let's find theta. I'm losing my numbering system. I think I called that step 3. Great. To find theta, well, just go back here. Tangent of theta. And I forgot to mention it, but it's actually common to call this phi instead of theta. It doesn't matter what you call it. I just try to match notation with convention. But you can call this whatever angle you want. So maybe update it in your notes. Tangent of phi. Again, it's just convention to call it phi. October, don't you dare claim that. Tangent of phi is opposite over adjacent, which is just negative 4 over 6. So phi is the arctangent of this, which is just negative 2/3. What's the arctangent of negative 2/3? I have no idea. It's about this many radians. About negative 33.69 degrees, or about negative 34 degrees. And remember before, we converted sine to cosine because cosine's convention for these particular solutions, these forced responses. But luckily, since we were looking at the real part, we already have it in terms of cosines. So we don't have to convert it this time, which is quite nice. And again, right, we replaced theta with phi. These are the same thing. I'm not going to update it everywhere. I'm just going to say they're the same thing. So we get our particular solution is 2 over root 13 times the cosine of 2t plus a negative 34 degrees. And I'm going to be very clear. The book uses degrees, and that's fine. I want to match that. There are a lot of reasons to use degrees. Please write the degrees here to make it very clear what is happening. Okay? So that's our particular solution. We combine our particular solution with a homogeneous general solution to get our general solution, and this will be step 4. Y of t was the homogeneous solution, which we said was k1 e to the negative t cosine of 3t plus k2 e to the negative t sine of 3t plus our particular solution, which was 2 over root 13 cosine of 2t minus 34 degrees. That is our solution, and it only took 20 minutes. Less than 20 minutes. Notice, by the way, that the period for the natural response is different from the period for the forced response. Which makes sense. The period for the natural response depends on the damping and the spring constant. It's what would this period be if nothing was happening to it. In this case, it's faster than the forced, than the forcing function. This period comes from eigenvalues, whereas the period in the steady state solution comes from the right-hand side, the forcing function. And remember, just like I said before, the forcing function is not the same thing as the forced response. They are related. Notably, they will usually have different amplitudes and phase shifts, but will have the same period. And there's lots of things that you can say about this, but I'm going to try to not say it right now because we have another video to talk about the solution. The whole point of doing this big example, well, there were 2 points. One was to show you how to do one of these problems from start to finish, and 2 is to prepare it so we can use this for more qualitative analysis and looking at phase portraits that are generated with numerical methods. So you've done the hard work. The next video is just sit back, relax, and enjoy the show. Give yourself a pat on the back. Nice.